Just vehicle. So to select for the AM, I'll just press it once. But I do not have the antenna connected, and even if I do, there is no AM radio station in my local area, so I'm not going to use it. So, and that's it.
This is a fully functional multi-band radio system built around the SI47 radio IC family with Bluetooth audio switching, LCD feedback, and a unified control interface. The goal of this project is to combine radio reception and Bluetooth audio playback into one system, controlled through a single embedded platform. In this video, I'll explain how the system works from a high-level perspective and how each part is connected together. Before going into circuit detail, it is important to understand the system as a whole. At the center of the system is a microcontroller. The microcontroller used here is the ATMEGA328P, which is the same found in Arduino development board. In this project, I am using the bare chip instead of the fully Arduino board to keep the final design compact and more integrated. A microcontroller is basically a small computer. It receives input, processes it, and produces output. In this system, it acts as the central control that coordinates everything. The microcontroller communicates with several components. The SI4732 radio IC, which is the one that I used in this project. LCD display, which is the 16x2 Bluetooth module, rotary encoder, and the audio amplifier IC. Most of the communication happens through I2C and GPIO control. Both the SI4732 radio IC and the LCD display share the same I2C bus. Even though they use the same two wires, each device has its own unique address. This allows the microcontroller to control multiple devices on the same communication line. The SI4732 is a digital radio receiver that supports FM, AM, and shortwave band, unlike its SI4735 families. Instead of processing radio signal in the microcontroller only sends control command to the radio IC. The radio IC chip then handles all RF processing and returns the audio output. These commands are based on the SI47 family communication structure defined in the datasheets. The system communication between the radio chip, the LCD display, and the master device is known as the I2C. I2C is a simple but very powerful communication protocol used to allow different electronics components to talk to each other using only two wires. These two wires are called SDA, the serial data, which carry the data, and SCL, the serial clock, which carry the clock signal. What makes I2C very powerful is that it allows multiple devices to share the same two lines as long as each device has a unique address. This means a single microcontroller can communicate with many different modules like sensors, display, radio chip without needing a large number of pins. The system works in a master-slave structure. The controller acts as the master, meaning it controls the timing of the communication using the clock line. The other device acts as slave and only responds when they are addressed. Communication starts when the master sends a start condition, followed by address of the target device and a read or write instruction. The receiving device then acknowledges and the data is transferred in a small 8-bit chunk. At the end of the communication, a stop condition is set to release the bus. One important detail in I2C design is the use of pull-up resistor on both SDA and SCL lines. Since the lines are not actively driven high by the device, this resistor ensures that the signal returns to a stable high state when no device is pulling them low. Overall, I2C is widely used because it reduces wiring complexity while still allowing reliable communication between multiple components. With a sensor, you might just write a value to a register or read a value back, but this is where the radio chip is different. It doesn't just use a simple register to read or write operation. Instead, it works using a command-based system where the microcontroller sends the command, followed by argument, and then wait for a response. I2C is still being used, but only as a transport layer to send this command, and it is clearly described in the datasheet. Instead of writing to register, I actually send commands and each command can have arguments and responses. So according to the datasheet, commands are used to control action like tuning or powering the device. Each command is just 1 bit in size, but it can have multiple arguments, and these arguments are used to modify what the command does. After sending a command, the chip responds with status information. Now, this table right here is the most important part because it shows a real example of how tuning actually works. So first, we send the command bit, which is 0x30 in the hexadecimal form, and this represents the tune frequency command. Then we send the argument, and this is where the actual frequency is defined. These 2 bits here combine to form the frequency value. In this example, it represents the 101.1 MHz. Thus, instead of writing a frequency directly, I'm actually sending a command followed by data that tells the chip what to do. And after the command has been sent, the chip responds with a status bit. And one of the most important bits here is the CTS bit, which means clear to send. Thus, I have to wait until the bit becomes high before sending the next command. Now, if we look at this from the I2C level, all of this is just being sent as a sequence of bits. Please note that to switch between these 4 modes, you need to repower the chip. That is, you need to send a power up command and set the properties based on which mode that you want to enter, whether it's the FM transmit, FM receiver, or the AM SW LOW, that is the general AM radio receiver, and the WB, which is supported by some of the SI4732 lab families. Also know that when, for example, in FM mode, you cannot send AM tune command or any command on the AM band. That is, when in the FM mode, the chip can only accept command that is from the FM mode. So if you are in FM transmit, you are going to be sending FM transmit. That is why you have to power it up and set properties based on that, because the chip cannot respond to any other command while it is in another command. All the command that is sent has to be in the current command that the chip is being on. The microcontroller start communication, send the address, then send the command and argument, and after that it read back the responses from the chip. And this table will show all the available commands like tuning, seeking, reading signal quality, and setting properties. So depending on what I want to do, I just send the corresponding command with the right argument. However, the interesting thing is that I don't actually write all this code manually. Using the PU2CLR SI4735 library, I can be able to send a simple functions like when I call radio.setup, the library is already sending multiple commands in the background, and when I set the frequency, it automatically builds this exact command structure we just saw. At the end of the day, communication with this chip is just a sequence of command and responses, and once you understand that, the entire system becomes much easier to control and debug. It is important to be careful when connecting the MCU directly to the radio chip I2C boards, because both operate at different voltage levels. Thus, connecting the radio chip directly to the I2C line seems to be an obvious choice. A level shifter is used between the microcontroller and the radio IC because they operate at different voltage levels. This ensures safe and stable communication between both. For example, the ATMEGA328P might be running at a high level voltage like 5 volts, while the radio chip, the SI4732 in this case, might be running at lower logic voltage, typically around 3.3 volts. Thus, if we route them directly, the 5 volts coming from the microcontroller might overstress the input pin of the radio chip, which can lead to an unstable communication. In other words, we need something in between the communication lines, and this is where the level shifter comes into play. In this project, because communication happens over I2C, we need a level shifter for both lines, the SDA serial data and the SCL serial clock. For the radio chip, the LCD display can handle 5 volts, so we didn't need to worry about it because the LCD can run on 5 volts, the same voltage with the microcontroller. However, the radio chip may not, and it is important to implement the level shifter. Now, one very clever way to view this is by using an MOSFET, commonly something like a 2N7002 or BSS138. At first, it may look strange because MOSFETs are usually known for switching power, but here we use one as a bidirectional logic translator. Here is how it is connected. The gate is tied directly permanently to 3.3 volts. The source connected to the low voltage side, that is the radio IC chip side. The drain is connected to the high voltage side, that is from the high voltage side, which is from the microcontroller and the LCD side. And both sides have their own pull-up resistor. However, for the pull-up resistor on the microcontroller, the LCD already have a pull-up resistor, so I'm not going to introduce an external pull-up resistor because the LCD I2C, the display configuration module, we handle the pull-up resistor, so I did not add a pull-up resistor on their side. But from the radio IC, I think, yeah, I do add a pull-up resistor, which is part of the level shift circuits. One pull-up resistor pull the low side up to 3.3 volts. Another pull-up resistor pull the high side to 5 volts. To understand how a MOSFET works as a level shifter, we need to understand what is inside it. An traditional MOSFET is built on a P-type semiconductor substrate, which is usually silicon. Inside this P-type body are two heavily doped N-type regions. One forms the drain and the other forms the source. Above the body is the gate, separated from the semiconductor by a very thin insulating oxide layer. This oxide insulation is why it is called a metal oxide semiconductor pure transistor. In most small MOSFET devices used for level shifting, the body is internally connected to the source terminal. This creates a natural PN junction between the body and the drain regions. Electrically, these behave like an internal diode called the body diode. When using a MOSFET and its push button devices, we use push button here to simulate the open drain of the master device and the slave devices. At ideal state, both devices are in high impedance mode, so the pull-up resistor defines the line as high. Now I'm pulling the low voltage side to ground. This creates a voltage difference across the MOSFET gate and source, which turns it on. As a result, the low state is transferred to the high voltage side. When I release the button, the device enters high impedance state and the pull-up resistor restores the line back to high. On the other hand, I am simulating the high voltage side, pulling the line low. The MOSFET automatically allows level to propagate to the other side. Once both devices release the line, the system returns to idle state and the pull-up defines the high level again. What this demonstrates is that in open drain communication system, the device never drive high. They only pull low or release the line, and the pull-up resistor will define the high state. The MOSFET acts as an automatic bridge that allows this behavior across different voltage domains. Please note that the threshold voltage between the gate and the source is crucial for this kind of circuit to work. That's why it is recommended to use a dedicated transistor, which is BSS138 is good enough and can do this job very well. And by this MOSFET trick works very well in this circuit. And if you're using another microcontroller, maybe something like an ESP32, this also applies to them as well. I think ESP32 specifically run on 3 volts. This kind of level shifter is not useful in this case. However, for the ATMEGA328P, it is designed to run at 5 volts normally. In other words, you need a level shifter for it. And that's pretty much more about the level shifter. And to the next is the audio amplifier that I use in this circuit. For the audio amplification, I use the SDA audio amplifier IC. It's a Class D audio amplifier that works very great in this project. And also, for designing the antenna schematic, you need to choose those components carefully. This is how I designed the antenna. Notice how a 4.7 microhenry inductor is running from the wipe antenna to the AM through the 0.47 microfarad capacitor, and we have the 180 microhenry inductor from the reference ground to the same AM through the 0.7 microfarad cap. And this 180 microhenry inductor is the antenna for the AM radio, and we have the 180 nanohenry inductor with the 18 picofarad capacitor, which acts as a high pass filter for the FM in. And these values we are carefully choosing based on the AM383 datasheet. Now, the system also includes a Bluetooth audio mode. Instead of designing a Bluetooth system from scratch, a Bluetooth module is salvaged from existing device like headset or small audio receiver. These modules are not fully programmable. They behave like a black box system. Different Bluetooth modules may behave differently. In most cases, a single button can handle multiple functions such as short press for play or pause, long press for power or wake. But this behavior is not standardized, so it depends on the module used. Since we cannot directly program the Bluetooth module, we simulate button press using MOSFET controlled by the microcontroller. Please, it is important to note that the Bluetooth part of the radio system is not included in the main idea of building the radio. However, it is implemented to increase the usefulness of the radio. Thus, a user can find it useful in most cases, while still on the control interface. The MOSFET controlled by the microcontroller acts like an electronics finger that presses the button for a controlled amount of time. This allows us to trigger, play or pause, or wake up behavior. The Bluetooth module is powered using a controlled power line. A MOSFET is used to switch the power supply on and off, instead of relying on an internal shutdown behavior. The system simply removes power externally when switching mode. It's good to know that the entire system is controlled using a single rotary encoder. The rotation controls frequency and volume depending on the mode, and the push button is used for different purposes such as the mute, mode function, volume selection, and Bluetooth activation and deactivation also. And that's how the rotary encoder pretty much controls everything using both the bounce switch and the rotation of the shafts. So after writing the code, which I will be explaining in my next video, I built the hardware and put together the necessary things, then upload the code. First of all, I bought the bootloader for the first chip of the ATMEGA328P and upload the code using some procedures. If you want to know how I uploaded the code on the first chip of the ATMEGA328P and the rest, I think you need to watch my next video where I will be explaining the details of the code, because everything cannot contain here because of the video is going to be a little bit longer. And thanks for watching. If you like the video, I think you can support the channel by subscribing, and I thank you all for your support, and I will see you in my next video.
So to select the volume, I need to